So yeah, thank you for the invitation to present the HRPD-X upgrade. I confess to being somewhat intimidated to be the first off the blocks, but we'll see if we can do something vaguely interesting. As you mentioned, I hold the RAN Research Chair in Electrochemical Devices in the Department of Materials at Imperial College London, and I have been a long-term user of HRPD, having first used the facilities down probably in about 1998, 99, something of that nature. So a long-standing relationship with HRPD and with ISIS more generally. I thank the team at HRPD for providing a lot of the information that I'm going to present to you today. Obviously, we're here as the user champions, essentially, so we're not the experts in the instrument design. So I'll thank the team there for providing the information. I'd also point out that, as well as being the chair at Imperial, I also sit on the EPSRC Capital and Infrastructure Strategic Advisory Team, which considers all of these types of proposals and feeds into the Infrastructure Advisory Committee at UKRI. And from that experience, I can clearly state that it's really important in these types of processes that community engagement and the user demand is demonstrable. And that's one of the things that the infrastructure advisory teams are really interested in demonstrating. So this is fantastic and really gives us that impetus to feed into that infrastructure team. So I guess there's a range of users in the meeting today, not all HRPD users. So it's probably useful to start with what is the existing instrument, what is HRPD? So as mentioned by Sean, it's the high resolution powder diffractometer, and was one of the original instruments installed on TS1 back in 1984. And the main advantage here is the high resolution, the delta D over D resolution. And this is an instrument which sits with a flight path of 95 meters. So it has very high resolution, particularly on the backscatter bank. So that allows the high precision determination of lattice parameters. It will look at subtle phase transition, looking at both pressure and temperature, complex line broadening phenomena, and you can also use this for the ab initio structure solution. So you can get to some low symmetry systems and some large-ish unit cells. So that's the existing instrument. And as Sean mentioned, it had an interim upgrade a few years ago. So the instrument itself currently has 2.5 square meters of detectors, zinc sulfide scintillators, backscattering at 90 degrees, and the helium tubes in the forward scattering. That's the schematic of what the current setup is, which I'm sure will be very familiar to those of you that have used HRPD, with the detector banks here, and the sample tank in the center there, with the beam coming from the left of the image. And so the proposed upgrade will involve a very nice new hutch. So the building on the left here is the proposed new HRPD, essentially at the same location as the existing facility. But the upgrade to the instrument is that we'll have a much larger area of detectors, so 17.5 square meters of detectors with an additional bank. So going from the 3 existing banks to a new bank being introduced, an intermediate. And in terms of what this offers, so as was outlined, this is one of the proposals which is fairly well advanced. So the upgrade would be looking to start in 2023 with commissioning in 2024. And the key takeaways are that you'd have improved capability at these longer D spacings, which allows you to tackle the more complex structures. So by way of just comparing the instrument capability that we currently have with what the proposed upgrade would be. So the summary of the current status, and this is taken from publications from the HRPD team, which will be available through the Endeavour program website. So you can see the 3 banks that we currently have. So the high resolution backscattering bank and the 2 slightly lower resolution, the 90 degree and the low angle banks. Okay, so the key take home here is that the really very high resolution of this backscattering bank. So then what we're looking to do is extend, as I said, from the 3 banks to the 4 banks. So the backscattering bank, the theta angle changes just a fraction, but the resolution is maintained. Introduce this extra intermediate bank with reasonable resolution here as well, whilst maintaining the resolution at the low angle. And in terms of the detector coverage, we can see the increase in the detector coverage in comparison with the existing state of the art. So that's the numbers as to what the upgrade will provide. In terms of how that translates, so what we're looking at here on the left is the current range of despacings that the HRPD instrument will access in the different time of flight windows. And one of the key phenomena you can see here is that there is a little bit of a gap in the coverage when we go down to this 100 to 200 microsecond time of flight window. We can also see that the current limitation is really down to about 15 to 18 angstroms in despacing. With the proposed upgrade, we're extending that despacing window significantly out to sort of 45-ish at this 100 to 200 microsecond window, but also we're closing this gap. There is no gap between the detector coverage. And in doing that, we're also not losing any resolution. So we're maintaining the resolution of the instrument, maintaining the resolution of the banks whilst extending the despacing range, which we will cover. Okay, so that's my understanding of the highlights of the upgrade. And what does that really mean for us as users? And I think essentially, taking essentially direct quotes from Dominic here, that effectively we should get about a 5 times increase in the count rate in the backscattering. And so therefore you can either go to much smaller samples, so about 5 times smaller and collect the same times, or get the same sample about 5 times more quickly. So we can start to think a little bit about how that will impact on the type of measurements and the type of science we can do. And of course, the other aspect is the expansion of the low angle detectors. So you can get the weaker features and get the statistics a little bit more quickly on those low angle detectors. So significant increase in capability in the backscattering and allowing us to also obtain these weak features. Okay, so that's my take homes, and effectively what does that mean in terms of the types of science that we'll be able to do? So in my thematic area for clean energy, we're interested in energy conversion and storage mainly, and so that's looking at the batteries, electrolysis and fuel cell materials, and increasingly looking at other energy vectors, and particularly looking at things like ammonia, nitrides, and so on and so forth. So the sample tank will allow us, the change of that will also allow us to think a little bit about the type of environments that we can use. So developing further in situ and operando capability, allowing us to undertake measurements more rapidly. Does that allow us to do slightly more detailed kinetic type measurements? The small samples is obviously good for those kinetic measurements as well. Data collection time, huge increase there, but also allow us to access these complex structures. So some of the modulated materials we've been working on at Imperial, but also some of the work that Sasha, for instance, has been doing with things like hexagonal perovskites, particularly for the electrochemical measurements. So a couple of examples of things that we are interested in doing and challenges that we have currently in some of our materials. So one of them is in this area of looking at ammonia as an energy vector and looking at nitridation and nitride materials and looking at kinetics. So one of the things we'd certainly be interested in is looking at in situ operando measurements of these materials synthesis. So this is looking at an oxynitride material. So this is the simulation of layering and swapping. So looking at the oxygen and nitrogen positions and which is more energetically favorable. And of course, these are linked to the synthetic process, but also thinking about its stability. So being able to switch gases and, I guess, thinking about exhaust gas analysis more rapidly and effectively will allow us to really follow how these materials are functioning under these types of conditions. And this is an area which is, if we can think about these nitride synthesis and characterization, the green hydrogen market, we're looking at for ammonia about 80 billion. So it's a significant market to target. And so the data here is existing data we have from one of our oxynitride materials, which recorded on GEM Express. And you can see that, yes, whilst it's a nice fit and we've got a good model out of this, and we've published this in Chem Matter, there is a degree of broadening of these features, some asymmetry potentially, and getting these higher resolution data more rapidly whilst doing this in situ would be ideal. So this was a measurement that was made under standard vacuum conditions, whereas actually it would be really quite nice to follow these transitions from the oxide to the oxynitride dynamically in situ under the synthesis conditions. So that's one area that we'd certainly be interested in looking at, and the new capability would give us that opportunity. And further things that we've been looking at are in the ion transport membrane area. It's a paper that's just been submitted by one of my students, Gigi Xia, where we're looking at the effect of humidity on transport, and particularly ion transport and oxygen vacancy content in ceramic oxides. And these are some of the HRPD data that we've recorded, looking at different annealing conditions. So under just sintering and annealing under wet oxygen, wet and water vapor. So these are two subtly different conditions, which has a significant impact on the overall oxygen diffusivity. And we think this is due to subtle differences in the vacancy content, and that is particularly challenging to ascertain. And certainly from the data we've got so far from HRPD, it's not entirely conclusive. So getting some higher quality data and being able to do these measurements dynamically. So these were all on pre-annealed samples, but doing these measurements in the water vapor condition, possibly with D2O as well, would certainly give us additional insight into how this impacts on the diffusivity of these materials. And then the further area that would be of interest to us in particular, and to the energy materials community, is increasingly it's apparent that we've looked at very simple structures and very simple systems, three-dimensional ordered systems, whereas actually we can find significant ion transport in particular in increasingly complex systems. And this is some work that we published last year, looking at modulated, both commensurate and incommensurately modulated oxide structures, and looking at their ordering of their oxygen positions, and thinking about how we resolve this in three-dimensional, 3 plus 2D dimensional superspace. So this was a material with niobium tungstate, which we can then start to see the superstructure reflections highlighted here as well. And so we can correlate that with the synchrotron. So you're getting some combination of measurements between the neutrons and the synchrotrons is great. In the synchrotron, we can really clearly see the superstructure reflections here, which can then feed into the detail in the neutron powder diffraction measurements. Now that's a complex measurement, and that takes a little bit of time. And when we're looking at some of these complex modulated structures, we're actually looking for the entire phase field and the space groups here, where we're going from modulated monoclinic structures to modulated tetragonal. There's a whole series of phase space here that would be fantastic to be able to explore. Having that significant increase in the data, or decrease, I should say, in the data collection time would really allow us to explore some of these phase diagrams in detail for these complex modulated structures. So a couple of examples of where I think we would be able to get some further insight and really utilize the upgrade for HRPD. And I think to summarize my understanding so far is that this is a program that will offer us enormous potential to tackle these increasingly complex samples, developing new sample environments and doing increasingly complex measurements in situ in operando, that then allows you to probe kinetics, reactions, phase behavior, and more. And essentially what we have to do is undertake this upgrade to maintain the leading position that HRPD has in worldwide neutron science. And with that, I think I will conclude. I think that's about my 15 minutes, so I will stop at that.